All right, this is number 6.25, where it says calculate the energy of a photon of electromagnetic radiation whose frequency is about 3 × 10 to the 14th per second. So the quickest way to estimate this is to use your electromagnetic spectrum chart in some common units. And we're told that it's 2.94 × 10 to the 14th per seconds. So we've got to find about 3 × 10 to the 14th. So find hertz on here. And 3 × 10 to the 14th, here's 10 to the 14th, here's 10 to the 15th. So we're a little ways into there, about 3 right here. Drop that down to the energy line, which is right here in joules. And it looks like we're right past 10 to the negative 18th, 10 to the negative 21st. So this would be 10 to the negative 19th. So something times 10 to the negative 19th would approximately be our energy. Well, we'll do the real math in just a second. We'll see if we come close, because remember, this is just going to give us an estimate. Let's go on to letter B, then we'll come back and we'll do the math for all of them. Calculate the energy of a photon whose radiation whose wavelength is 413 nanometers. So we want E equals h nu for this, for energy. The wavelength, remember, can come from the C equals lambda nu equation. And so if I want to find nu right here, it would be C over lambda. So this is equal to H times C over lambda right here. And it's given me a wavelength of 413 nanometers. So 413 times 10 to the negative 9th meters would go in for lambda right here, and then I'd have H times C here on the top, which I'll get back to in a second. But instead of doing all this math, you could estimate it by looking up 413 nanometers on here as a wavelength. So here's 100 in nanometers, here's 1,000 in nanometers. So right in between would be 500, 400 would be somewhere right about here. And it wants to know the energy, so drop it down right here, and we'd be 10 to the negative 18th approximately. So let's write that down as something times 10 to the negative 18th. It might be at some big number times 10 to the 19th, but we'll see what it ends up being after we plug these numbers in to get it. And then letter C, it says, what is the wavelength of radiation whose photons have an energy of 6 times 10, 6.06 times 10 to the negative 19th joules. So now it wants to know what is the wavelength. So let's find the energy, 10 to the negative 19th. Here's 10 to the negative 19th. It's a little larger than that because it's 6 times 10 to the negative 19th. So that would be halfway right here would be 5. So 6 right here. And then follow that line up to wavelength. So go up here to wavelength. It looks like in nanometers would be between 100 and 1,000. So maybe a good guess would be a little more than 500, maybe 600 nanometers. Well, let's do the math and let's find out for each one of those how close we came with our approximations. So in letter A, to do the math, calculate the energy of the photon whose frequency is. So we use the equation E equals h times nu. H, of course, is Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. I'm writing kind of crooked here. And then multiply that by the frequency, which is 2.94 times 10 to the 14th. So multiply those two guys together, and we end up with 1.95 times 10 to the negative 19th joules. Did we come close? Sure. We were in the ballpark. 10 to the negative 19th, 10 to the negative 19th. For a multiple choice set, and you had one that was like 10 to the negative 7th, one that was 10 to the negative 11th, one was 10 to the negative 13th, and one that was 10 to the negative 15th, 10 to the negative 19th, well, you'd choose the negative 19th because you would have been close to it already just with the approximate one. All right, letter B then. We already set up this equation, and instead of putting h in and c in, which we know h is this number, and c is, of course, the speed of light, 3 times 10 to the 8th meters per second, then we converted this to regular meters already. We would end up with, doing this math, 4.8 times 10 to the negative 19th joules. And we said it would be close to 10 to the negative 18th. Well, 4 times, this is almost 5, so this is like 5 times 10 to the negative 19th, and of course we'd be halfway towards 10 to the negative 18th, so we'd be like right in here. We'd be pretty close. be able to get ballpark anyway to it. And then letter C, it asks what is the wavelength of radiation. So wavelength right here, if you solve this equation right here for wavelength, wavelength would be equal to h times c divided by E. So hc we know from right up here. Plug those in, and then we put the energy in down here. Plugging those numbers in and doing the math on your calculator, make sure to use your exponents correctly. You'd end up with 3.28 times 10 to the negative 7th meters. 2 to the right to get it to nanometers, so it'd be 328 nanometers. Were we in the ballpark? Sure we were. We're 328 to 600, so we're somewhere between 100 and 1,000. We said we'd be close to that, so we're in the ballpark region of both of those by using the electromagnetic spectrum chart.